In this video, we will solve more probability problems using the help of contingency tables, the complement rule, tree diagrams. Let's start with contingency tables. A contingency table provides a way of portraying data that can facilitate calculating probabilities. A contingency table looks like this. We've seen this in the previous video already. You see the two variables, one variable right here, male and female, and the other variable for this specific example right here on the top, frequently, occasionally, not at all. Okay? Now, if you add all of these numbers in the first column, the frequently partial total will be 221 plus 207, so it will be 428. And this is the first thing you should do, find the partial totals for each column or row, if that is not given in the problem, okay? And then we will use the contingency table to help us solve and answer the following questions. Let's see, for the occasionally, I have 886. For the next one, 1,536. The partial total for this row for male is 1,472. For female is 1,378. And these are called partial totals. The same thing with these totals. And the grand total is actually the number that goes into this last cell right here. And this is the summation of all data. And this is called the grand total. This came out to be 2,850. I added these two numbers to come up with this. Now, if you continue adding these numbers, you will come up with the same result. If you add all of the numbers right here in the body of this table, you should come up with this result. So check that out. And let's continue now answering questions based on this contingency table. So first, let's read the problem. This is about charity. It says the table below shows the results of a survey that asked people whether they were involved in any type of charity work. A person is selected at random from the sample. Find the probability of each event. Here is the first question. The person is frequently or occasionally involved in charity work. So we have to look at frequently, occasionally, and keep in mind we have or right here. So I will be thinking at the addition rule and the fact that these two events are or are not mutually exclusive. So let's write down the formula. Probability of frequently, and I'll simply use the words here, or occasionally, is probability of frequently plus probability of occasionally. And the general formula tells us to subtract the overlapping part if there is any overlapping part. So I'll simply write down the formula as it is, the general form, and then inspect what's going on. Frequently, I have this partial total, which is 428, and this will be out of the total number, the grand total. Occasionally, I have this partial total, which is 886, out of the grand total. And let's see, do I have any overlapping part? Do you see these two columns having an overlapping part? The answer to that is no. So these are mutually exclusive, meaning the probability of frequently and occasionally is 0. So our final answer will be the result of adding 428 and 886 divided by 2,850. After you simplify, the final answer should be 219 over 475. Now let's talk about the second question. The person is female or not involved in charity work. So let's just look at this event being a female and then not involved in charity work and the connection word, which is or. So again, we are dealing with the same rule, the addition rule. So I'll simply try to write down what that means and look at the correct values in the table. Female or not involved. I will simply write down the rule, female plus probability of not involved in any charity work minus probability of both. So let's see. What is the probability of selecting a female? I will be looking at the partial total, which is 1,378 divided by the grand total, which is 2,850. Plus, I'll be looking at this column, which is not involved at all. And this is the total number there, which is 1,536 divided by the grand total, and then minus, and then looking at these two columns. Do they have anything in common? You do realize that the overlapping part here is this cell, which is 741, which I added once for the not at all column and once for the female column. So I must subtract these ones. So I will subtract 741 divided by 2,850. Okay? Because these two are not mutually exclusive. The answer here will be 2,173 divided by 2,850. And we will try to simplify. It seems that the simplified fraction form stays this. So this will be the answer. The next question is, are the events being female and being frequently involved in charity work mutually exclusive? You'll have to remember what mutually exclusive events are and look at these two events, being a female and being frequently involved in charity work. In other words, do these two events have something in common? If these two events have something in common, they are not mutually exclusive. Let's just take a look at being a female, which is right here on this row, and frequently involved in charity work, which is right here on this column. You can clearly see that these two, the row and the column, have something in common. So they share common outcomes. Because of this, the answer is no. And you just say not mutually exclusive, since 207 of female are frequently involved in charity work, which means probability of these two events is not zero. Probability of being a female and frequently involved will not be zero, will actually be 207 divided by 2,850 if we were to find it. Scrolling down, we will answer more questions, and this is the reason I actually copied this table to a side. So let's just take a look at the next couple of questions. Next question, what is the probability that a person is female and not at all involved in charity work? We look at the word and, okay? We know that if we were to apply the rule, we will apply the multiplication rule. However, because we're dealing with a contingency table, it's actually a lot easier to do this type of problems without applying the rule. Probability of being a female and not at all involved in charity work will guide us to the overlapping part of these two events. Female right here on the row, not at all involved right here on the column. So probability of both is actually 741 divided by 2,850. So you simply take a look at the overlapping part, which is 741 divided by the total number 1,350. So I'll just simply write it down. Probability of a female and not involved. Next question. Probability that the person is occasionally involved in charity work, given that the person is a female. So we are looking at occasionally column. We are looking at this word given, and then we are looking at the second event, which is female. I'll simply write this down, probability of occasionally, then given female. Let's just apply the rule for the conditional probability. This means probability of both on the top, occasionally and female, and on the bottom, probability of selecting a female. So we are looking at both occasion, which is right here on this column, and female, which is right here on this row. Here we have the 430. So that will be 430. And on the bottom, I have female. So for female, I'm just looking at the total, partial total for female, which is this number right here. This is a conditional probability. It will not use the grand total. It will use partial total. Which partial total? Well, the one that is corresponding to what is under the condition or related to the condition, which is 1,378. And we can simplify it, and that will be the answer. Let's just take a look at the next one, which is very similar. probability that the person is a male. Again, given that they are not at all involved in charity work. So to answer this question, we will apply the formula in a very similar way. And on the bottom, I'll be looking at this, not involved. So let's just take a look at those numbers in the chart. Male and not involved right here, male right here. Both will actually have this number, which is 795 on the top, okay? And on the bottom, not involved. I'm looking at not involved, the partial total corresponding to not involved, which is this one this time, which is 1,536, okay? And you will simplify this if it can be simplified, and that will be the answer. And here is the last question related to this contingency table. Are gender and level of involvement in charity work independent? In other words, is one event occurring affecting the probability of the other event occurring? So how do we check independence? Well, this is how we check independence. Probability of one event, let's just say being a male, given that he is or he is not involved. Let's just try to look at the last example. Is this the same as probability of just being a male? In other words, being or not being involved will have an effect on the probability of choosing a male from this sample. Let's see. Well, probability of being a male, given that he is not involved, is 795 divided by 1,536. And probability of being a male, it's actually total number of males. Let's just look at the table for 72 divided by 2,850. This is just the formula for probabilities. If you do the math, you realize that these two are not equal, which means that the probability, the occurrence of one of the events will affect probability of the occurrence of the other, which means these are dependent, not independent events. And you can look at another gender, like a female, you have the results above and check that out too. So the answer to this question is that these two events, gender and level of involvement in charity, are dependent. Let's now take a look at this problem involving another contingency table, and we will answer all of these 4 questions. Healthcare for dogs. The table shows the results of a survey in which 90 dog owners were asked how much they had spent in the last year for their dog's health care and whether their dogs were purebred or mixed breed. Right here we have the type of dog, purebred or mixed breed, and how much money they spent, less than $100 or $100 or more. Right here we have the partial total for each one of these rows, columns, and here we have the total, which is the grand total, which is consistent with what is given in the problem. So let's answer these questions. First question, find the probability that 100 or more was spent on a randomly selected dog health care in the last year. In order to answer this question, we look at this category, which is 100 or more. And 100 or more is actually corresponding to a partial total of 50 out of the grand total. So the probability of spending 100 or more on a dog is actually 50 divided by 90, which will be 5 out of 9. And this is the answer. The second question, given that the randomly selected dog owner spent less than $100, find the probability that the dog was a mixed breed. We have a condition here given, okay? So be aware of these keywords. And we are looking for less than $100 and a mixed breed. So let's see, how do we write this down using the corresponding symbol? So the probability that the dog was a mixed breed, I'll write down in words, mixed breed, given that the owner spends less than $100. So this is how it looks like. And by simply applying the rule for conditional probabilities, you have to put on the top both events. So we are looking for the mixed breed and less than $100 spent. And on the bottom, you have to look for what's right here on the bottom. That is the condition, okay, which is probability of the owner spends less than $100. So let's take a look at the table, mixed breed and less than 100. And I'll use this color, less than 100 mixed breed. We have this overlapping part, okay? And probability of less than 100, this is a conditional probability. For conditional probability, the sample size is adjusted. We will not be using the grand total, okay? So I'm looking for less than 100 partial total, which is right here, and that will be 40. So the answer to this problem is 21 on the top over 40 on the bottom. Next question, find the probability that a randomly selected dog owner spends $100 or more on healthcare and the dog was a mixed breed. We're looking for this connective word, which is and. So for this problem, and I'll write down the answer right here for C, simply write it down again in words. Probability that the dog owner spends 100 or more. So I'll just have this category 100 or more and mixed breed. And contingency tables, probably the easiest type of problem with contingency tables because we simply have to add the overlapping part, 100 or more and mixed breed to be this number. And the total number will go on the bottom. So the answer is 15 over 90, which simplifies to 1 over 6. And the last question, are the events spending $100 or more on healthcare and having a mixed breed dog independent or dependent? In other words, is one occurring affecting the chance of another one occurring? I will simply check if probability that spending $100 or more, given that the owner has a mixed breed, is the same as probability of spending $100 or more. If it is, that means second event, which is mixed breed, doesn't have any effect on the owner spending $100 or more. Well, the answer for spending $100 or more is actually the answer to the first question. We have it right here. So this will be 5 over 9. What is the answer to the first part, to the first probability? Well, I will take it right here. So the answer to the first part, let's just put it right here. Probability of $100 or more, given that the dog is a mixed breed, equals probability of $100 or more and a mixed breed over probability of mixed breed. Probability of $100 or more and mixed breed is actually 1 over 6, right? Or 15 over 90. I'll be looking simply at the intersection of these two and I'll put that on the top. And mixed breed, I'll be looking at the partial total for mixed breed, which is 36. 15 over 36 is the answer to the conditional probability. 5 over 9 is the answer to spending $100 or more. So coming back here, I want to know if these two are equal to each other or not. I have 15 over 36, and I put a question mark, 5 over 9. We can clearly see that these are not equal to each other. 15 over 36 simplified by 3, you'll actually have 5 over 12. 5 over 12 is not equal to 5 over 9. So it seems that being the owner of a mixed breed has an effect on spending $100 or more on healthcare for a dog. So these two events are dependent. The next type of problem is related to the complement of an event A. And we learned on the previous video that the complement of an event A consists of all outcomes not in A. The best way to visualize this, and we did show that, is using a Venn diagram. And in this Venn diagram, if you look at A as this circle, all the events in A are in this circle. The complement of the event is what's not in this circle, but it is in the sample space. And this is the visualization of the complement of event A, which is A prime. Just for you to remember the rule that is very important and we'll be using in many problems is the fact that the probability of A plus the probability of its complement equals to 1. Note, at least 1 means the value of 1 happening, or 2, or 3, or 4, or n, when there are nth trials. This is a very important expression. We will see many problems related to this expression. So let's take a look at the next example. The probability that a particular knee surgery is successful is 0.85. What is the probability that a given surgery is not successful? In order to find out what is the probability that a given surgery is not successful, you'll simply apply the complement rule and you write down probability of not being successful would be 1 minus probability of being successful. This is the complement rule, right? So if we say A is a successful knee surgery, this is the event. And let's just call it success. Now A prime will be not success. You simply apply the rule. So probability that a knee surgery is not successful based on this given information will be 0.15. Next question. If 3 knee surgeries are performed, are these events independent or dependent? Why? So think of this. We're talking about knee surgeries performed on different subjects, on different people. So we are looking at this as independent events. The fact that one was successful will not affect the fact that another one is successful. So we are looking at this as independent events, even if the knee surgery is performed on the same subject. So I hope this makes sense. So we will say independent. The success of one doesn't affect the success of another. Find the probability that 3 knee surgeries are successful. So I will write down this probability of the first one being successful and the second one being successful and the third one being successful. So you see, I'm using and because I'm looking for all 3 successful, which means I'll be using the multiplication rule. And because these are independent events, I can simply multiply the probabilities, probability of the first one being successful, the second one being successful, the third one being successful, which is 0.85 times 0.85 times 0.85. So the final answer is actually 0.85 raised to the 3rd power. So the answer will be 0.614. Moving on, find the probability that none of these 3 surgeries are successful. Probability that we have none of these 3 surgeries successful will actually be probability of the first one unsuccessful and the second one unsuccessful. And I'm using the complement right here because the complement is not success or unsuccessful. And the third one being unsuccessful. So basically, I'm repeating the same thing that I've done at number 3, but this time I'm doing the same thing with none of these being successful. So instead of using the successful one, I'm using the unsuccessful. And the probability for each unsuccessful one is 0.15. So 0.15 raised to the 3rd power, 0.15 times 0.15 times 0.15. And the answer to that will be about 0.003. And now the last question, find the probability that at least one of the 3 surgeries are successful. Well, what does this mean? Let's just write this down, at least one. That means one or more, right? One or more. That means if you have 3 surgeries, you can have 1 successful, or you can have 2 successful, or you can have 3 successful, 1 or more. This one, it's something that it's kind of difficult to do. It's not impossible. It can be done with the addition rule. However, an easier way to do this problem is trying to figure out the complement. The complement of at least 1 successful is probability of none of this is successful. So in order to use the complement, I will simply subtract the probability of non-successful from 1, and that will give me the answer a lot faster and easier. So what I used right here is the complement rule. These two, probability of at least one successful and probability of non-successful, are complementary to each other, which means if I can find the probability of the complement, and yes, I already found the probability of the complement on the previous problem right here, non-successful, just subtracting that from 1 will answer the original question. So right here I have 1 minus 0.003, so that will be 0.997. Okay, so now you see right here how useful it is to make sure you understand what a list means, and to understand that if you have 3 surgeries, you can have only these outcomes: non-successful, 1 successful, 2 successful, or 3 successful. So if you have 1, 2, and 3 all in here, the other one, that's the complement, will be non-successful or 0 successful surgeries. I hope this makes sense.